So what are my research areas? I mean, I said that all my work has been in physics, and what am I doing in an electrical engineering department, right? My PhD thesis was based on nonlinear optical effects, and my central theme of my research is also nonlinear optical effects. Now, people study nonlinear optical effects in different contexts, and initially when I started my experimental research work, nonlinear optics was interesting, but then we did not have a source of light which could initiate nonlinearity. So my first work was on developing some sources of light so that I can initiate nonlinearity in fiber. Actually, we were looking at fiber medium, and that led me to the research area of fiber laser sources. So over the last almost 15 years, I've been working with developing lasers, essentially fiber lasers for continuous wave, tunable lasers, mode block lasers, Q-switch lasers. Recently, I'm associated with LIGO India for developing 2-micron lasers. They have very specific requirements on narrow line lasers at specific frequencies. We are also working on high power lasers. And it turns out that at some of these high power lasers, what really you can see is that you need to have a consideration of nonlinear optics in developing some of these lasers. Right? So that is my first or the original research area I started with. But then we started looking at being in an engineering department. We tried to find engineering applications for nonlinear optics. So my goal of studying nonlinear optics is to find specific applications for nonlinear optics. And that led me to Brillouin amplifiers, and also for multi-point dynamic and static sensing. And the idea here is that you have a long length of fiber laid across a bridge or along an oil pipeline, and let us say there is a temperature change or a strain change because of some external perturbations. How do you detect it as sitting at 100 kilometers away or 50 kilometers away? This is like a radar principle. You send a pulse of light, you interrogate the returning pulse, but here, unlike a radar, you also look at, unlike a conventional radar, you also look at the frequency shift of the light that is coming back. And any changes in the acoustic waves will give rise to a Brillouin effect. And I'm sure everybody is familiar with Brillouin effect. The frequency changes in an optical fiber in silica medium by about 10 gigahertz. And by detecting the change in frequency, you can find out what is the signature of the acoustic wave. So that's an excellent place where nonlinear optics can be used for an application. So that is one major part of the work. The other part of the work is again how to put use of nonlinear optical effects in an engineering application, again in an optical communication application. So that's where the whole plethora of opportunities for optical signal processing comes in. These are some examples of optical signal processing functionalities that I have implemented in the past, starting from wavelength conversion, which means that it's not second harmonic generation that I mean here. What this means is that, let's say, everybody knows that your optical modulation happens in different carrier frequencies. You have what is called as a wavelength division multiplexed systems. So let's say you're transmitting your signal through a particular wavelength, and at some network node, you find that the remaining network is actually busy with that wavelength. So what current systems do is they convert it into electrical domain and then go back to optical domain by modulating in the second wavelength that is free. But what if you can avoid that optical to electrical to optical conversion by directly transferring all your information from one wavelength to the other? That is wavelength conversion, right? The other one is clock recovery. I mean, you know that to make a decision of whether your bit is 1 or 0, you need to know the clock. You need to know where the transition points are. Currently, that is all implemented in the electrical domain. And as you go to faster and faster communication systems, electrical clock recovery becomes challenging, and that's where optical clock recovery comes in. Phase conjugation and phase sensitive amplification, a part of it I will be discussing today, so I will leave it open right now. The other project that we are currently doing is time stretching for photonic analog to digital converters. So everybody is familiar with analog to digital converters, without which the digital world does not exist, right? All the signals in nature are analog and all the processing happens digitally. And so there are these key analog to digital converters which basically convert my analog, for example, sound or speech or picture or data to a digital format so that it can be processed, it can be transported and so on. The challenge there is, again, as you go to higher bandwidth signals, the noise in this conversion becomes larger, and that's where we are trying to see how we can attach a photonic front end to an ADC so that the ADC performs very well. So that's a current ongoing project. Maybe at a future opportunity I will talk about our findings there. And to demonstrate all these optical signal processing functionalities, nobody is going to turn and look at my results if I do not demonstrate it for the current communication systems. And what is the current standard for communication system? We know that it is high speed coherent communication, right? So that led me to an independent kind of research area on how do you now keep increasing the speed of communication in an optical system. Optical fiber is supposed to have infinite bandwidth. Now, how do you actually make use of that infinite bandwidth? Is that bandwidth really infinite? Actually, no. So that led to high-speed communication system, and that also led to another interesting area, which is radio over fiber, which means you need this high speed only because you're digitizing all your information. But now, can I send my speech signal in the analog form itself through an optical fiber? And that is radio over fiber. So these are emerging area in communication. So this is my mind map for my research. And as I said, today's talk is going to be on optical coherent communication. What is the status and what is the need for optical signal processing? And I'll pick one case study for optical signal processing where I'm going to make use of optical phase conjugation for dispersion and nonlinearity mitigation. So I'll give you the simple theory for that, and how do we do that in a cost energy efficient manner, because ultimately if you want it to be deployed in the communication system, the final the final deciding factor is how much money you need to spend, what is the cost, what is the energy involved, right? So how do you do that in an energy efficient medium, and of course demonstration in an actual experimental link. So to tell you what is the status of optical coherent communication, I'll give you I'll tell you first what a coherent communication system is. Those who are very familiar with this, please bear with me. This is a very introductory slide. So we know the electric field, I mean our fundamental electromagnetic wave, and for convenience I have represented it as a plane wave here. Let me see if I can change the color of. Sorry, let's not experiment on it now. So you know that the electromagnetic wave is can be in two polarizations. So you could modulate your information in two polarization. That leads to polarization division multiplexing. You could send two independent information in two polarizations, and in the end at the receiver you separate out the polarization. Of course, there will be mixing, but then you assume that this mixing is linear, and any linear transformation we can invert if we know the transformation correctly. So that is polarization division multiplexing, and that's a way to increase the speed with which you communicate. And you also now, if you see what is the electric field, it has a phase and it has an amplitude. If you change the amplitude as a function of 1 and 0, that gives you the amplitude modulation. But then if you change the phase as a function of, you say that I would encode a 0 or a pi corresponding to my bit 0 or a bit 1, that gives you the phase modulation. And I could also change the frequency or wavelength, that is the frequency division multiplexing or wavelength division multiplexing. So in the current coherent communication systems, we are actually employing all these degrees of freedom. These are independent degrees of freedom to modulate our information. We modulate information independently in two polarizations, independently in amplitude, independently in phase, and also in different wavelength channel, right? So I can write this in a symbol form as in phase and quadrature component. So you see Ex e power j phi x. This is in the polar form. I can write it in the kind of Cartesian form as Ix plus jqx, or this I is the stands for square root of -1, so it has a real part and an imaginary part. And also I have e power j omega t I omega t minus kz. I mean, this is considering plane wave. Once it's in a fiber, we know that it's no more a plane wave. You will have the modal distribution and so on. I am not going to talk about mode division multiplexing, where you can now think of one more independent degree of freedom where you can put information in different modes, right? I'm not going to talk about that. So this is the status of the current optical communication system, where you start with a laser, you split it into two polarizations, and using these in-phase quadrature modulators, so you can basically modulate Ex and phi x, or equivalently Ix and Qx, and similarly Iy and Qy into orthogonal polarization. So you have digital signal going into both the polarization, right? And then you can combine them, transmit through the fiber, amplify them, and thankfully EDFA does not care whether your information is EDFA is erbium doped fiber amplifier, which is an all optical amplifier that does not care whether your information is in phase quadrature. It doesn't matter, right? And it does not care for the frequency also, for a range of frequencies. Now, what do you do at the receiver? Now, the receiver is slightly complicated than our regular on-off keyed receiver. You have to detect phase, and as students of physics, we know that the only conclusive way of detecting phase is through an interference, right? So you basically are making tiny interferometers in every coherent receiver. And what does it consist of? Of course, you need to split the two polarizations. For interference, you need a reference. So that is the reference laser or the local oscillator laser. That is also split to two polarization, because interference is sensitive to polarization. So you basically split the two X and Y polarization, and you allow it to beat in this device, which is a 90-degree hybrid, which is supposed to give you the in-phase and quadrature component of X polarization and Y polarization. And obviously this X and Y is not what you had transmitted, because the polarization has rotated inside in the channel. But then you send it to an analog to digital converter, you get bits corresponding to X polarization, Y polarization, X polarization and Y polarization, and you get your in-phase and quadrature components. And then you figure out what was the mixing between the two polarizations, and basically invert the mixing, and that's how a current coherent communication system. This is not a futuristic system I'm talking about. This system is in place for the last 10 years. Okay, the 100 gigabits per second, the 400 gigabits per second, which is a current standard. 100 gigabits per second was a standard about 10 years ago. This is the scheme where the communication system works. One thing to understand here is in an on-off key system, you have a 0 and a 1. This is the sequence that you transmit, and you can represent it in the IQ axis, or what is called as a constellation diagram, as a 0 and a 1, because there is no phase here. So there's nothing in the Q axis. So your symbol is either at 0 or at 1. Of course, I'm representing ideal symbols. This is at 0 and 1. But in case of phase modulation, what would it be? It will be a 0 phase or a pi phase. There is no amplitude difference. It's either +1 or it is -1. But if I do both amplitude and phase modulation, how does it, if I do 4 levels of phase modulation, because, the phase space is much more richer. So there's no restriction on actually imposing only 2 phases. You could impose 4 types of phases. That gives rise to what is called as quadrature phase shift keying. And now you have 4 independent phase levels with which you can modulate. And each of these 4 independent levels can now represent 2 bits, so that instead of in every bit slot, you can now, if this bit slot is sent at 45-degree phase, it means that you're transmitting a symbol, transmitting a bit sequence 0, 0. If this bit slot is, the next bit slot is sent at 90 plus 45, 135, it means it is 0, 1, 1, 0, and so on, 1, 1, right? So by doing this additional degree of freedom in modulating with multiple phases, what essentially you're able to do is to send more bits in one slot. Now, there's no restriction that you have to maintain the amplitudes the same. You can also have different amplitudes that will give rise to quadrature amplitude modulation and so on. So let's not get into the details. The point I want to make it clear here is that rather than dealing with ones and zeros, we are now dealing with constellation space. Now the constellation space becomes denser as you are transmitting more bits in the same bit slot. Okay. With this understanding, let's just go on and see where is optical communication system today. What is the status? So I'm sorry, I missed putting reference here. This is from Peter Winzer's Bell Labs work. This is a plot which shows the capacity over different years. There are two sets of plots here. One is for research, the other one is for products, and the products is product line is closely following the research line. So you have four lines here. These two lines, the pink and the red, actually shows the per carrier. Per carrier is in per wavelength data rates. And you see that we are around 2020. This paper was published probably in 2018. So at research, people had demonstrated per carrier 1 terabit per second. Okay, 1 terabit per second per carrier. Now, if you multiply it by 80 channels in a WDM system, that gives you here. That gives you the triangle here. So if you can replicate 1 terabits per second at around 80 channels or 100 channels, that will give you 100 terabit per second, and that's at the research. Where are we at the products? At the products, we are at somewhere around 400 gigabits per second here. That gets multiplied by about 80, and that gives you this plot. This increase in capacity over different years, you see there is a kind of slowdown in the path, and that's simply because we are not able to utilize the spectrum with more number of data. We are trying to approach what are fundamental Shannon limits, which actually talks about the capacity of any channel, right? Shannon's theorem, which was written by Shannon in 1948 or so, it says that if I have a channel with a specific signal to noise ratio, that's what is available, the capacity is mathematically limited by a certain number, right? I'm not going to discuss the details. And as years proceed, we are actually reaching that limit, and this is the capacity limit. And unless we do something drastically different, we cannot increase the capacity. Now, the question you want to ask is, do we really need this capacity? I'm talking about, 10 Mbps in my cell phone, right? Do I really need 100 terabits per second? But imagine that hundreds of thousands of people are using this cell phone with this 1 or 10 Mbps, and all that capacity finally is carried by an optical fiber in a long haul link. So this capacity requirement is not artificial, it is actually real. Especially now with the pandemic, everybody has started using internet for the meeting. Today also I'm doing a lecture from my through my computer rather than going to a physical class. So the capacity usage has been increasing, and I'm sure that in 2020, if you look at beyond 2020, you will see a large surge in the capacity requirement after 2020 because of this current situation, right? So this is the capacity trend, and where are we in our earnest effort at IIT Madras? What are our communication capacities? So all this requires high signaling rate. So it is in 2016 of December during the Varda cyclone is when we installed our high-speed optical test bed. It means that I have all what it needs is a digital to analog converter and an analog to digital converter, right? It's electrical capacities, electrical baud rate, signaling rate is that matters. So we had a high capacity. In terms of bandwidth, this would run at about 40 gigahertz bandwidth. Then you do all these additional modulation formats on polarization multiplexing, phase multiplexing and so on to increase the data rate, right? In a year's time, we demonstrated 256 gigabits per second with about 32 gigahertz of bandwidth, and we did a transmission of 2 data rates in standard single mode fiber. In a year's time, again further to that, from 256 we moved to 400 gigabits per second, and we also installed the first space division multiplex test bed. Now, what is space division multiplexing? Space division multiplexing is a solution to break the Shannon's limit, right? So I will not talk about it now, but then we installed this test bed, and we installed 84 gigabits per second. This is much smaller when compared to the earlier data rates, but then we are doing a 2-mode transmission. We are transmitting data in 2 transverse modes in an optical fiber. And this last year, before the pandemic, we demonstrated a terabit per second. We are somewhere here in 2020. We are delayed slightly with respect to the rest of the world, but not really delayed by a lot of years. What are the challenges now? I mean, why did it take so long, and why are we struggling? There are several impairments that come up when you try to do coherent communication. The first set of impairment is, at the laser. The laser, see, remember, we are transmitting information in phase, which means that my laser has to be strictly monochromatic. And you know by now that lasers are not at all monochromatic. They have a line width. They have a specific spread, frequency spread, which means the phase keeps moving on its own because of the poorer coherence of the laser, right? Which means if I have to reliably modulate my laser with phase, the laser should not change its phase on its own, right? So the phase noise of the laser is the biggest constraint. So you should pick very narrow line, ultra narrow line lasers for coherent communication. At the same time, the cost has to be low, because you and me are not ready to pay more money for our bandwidth, or if at all we want lesser money to pay for our bandwidth. The other issue is that, I told you that at the receiver there is another laser, and ideally the transmitter laser and the receiver laser should exactly match in frequencies for very good interference. But if there is an offset, it means that there is a frequency offset, and in time it is omega t, right? It is EPA j omega t minus beta z. So as time progresses, the phase that is omega t or delta omega t, that keeps adding. So as a result of frequency offset, instead of 4 constellation points that you sent, what you get is a circuit. So you've lost your phase information because of your frequency offset. Phase noise, I told you. So instead of one single phase, what you're getting is a spread phase as a result of phase noise. Now the channel, even though it's a fiber channel, fiber is not a really nice holy channel, because fiber introduces several impairments when you talk about coherent communication system. The first one is chromatic dispersion. Now what is chromatic dispersion? Different frequencies propagate with different time. So as a result of that, if you had sent in a pulse, all the components of the pulse are arriving at different times, which means the pulse gets spread. The pulse gets spread means that the amplitude distributes over time, and all the amplitude is messed up. So you see, you had sent in only one amplitude, but because of dispersion, you have the constellation that is completely full because of chromatic dispersion. Then you have polarization mixing. So when I show the constellation at each of these stages, I'm assuming that only that impairment is present. So you transmitted 4 constellation points for X polarization, you transmitted the same for Y polarization, but imagine they are mixing. And when they mix, this is the situation. This is what happens. You will have a constellation corresponding to X, you will have a constellation corresponding to Y, falling on top of each other. So instead of 4 points, you will get multiple points here, in fact 16 points. So that's polarization mixing. Then you have polarization mode dispersion, which means that the 2 polarizations need not travel with the same speed. They walk off at different speeds because of some residual birefringence in the fiber. And the problem is that this residual birefringence is not, it's a statistical quantity. It depends on the several extraneous factors. So what you get is some kind of spread here. So these are channel impairments. And you have nonlinear effects. You have nonlinear effects because as you increase the power, or even though you are transmitting at low power, the intensity of light in an optical fiber is high because the cross-section area is small. And when you have large intensity, you have self-phase modulation and cross-phase modulation. And the consequence of self-phase modulation or cross-phase modulation is that the phase gets distorted and your information is encoded in phase. So when you have a distorted phase, you cannot basically retrieve that phase in the demodulation state. So these are the different challenges in coherent communication, whether the moment you go beyond 10 gigabits per second, the moment you go to 100 gigabits per second or higher, you have to address all these challenges. And all these challenges are easily resolved because we know exactly why that is happening and how the mechanics, the physics of each of these processes, we know exactly. So all what we need to do is to write down signal processing algorithms, which will basically reverse all these processes. If I know that the chromatic dispersion is going to delay this way, I apply a signal processing algorithm in such a way that the frequencies are taken back, right? So I basically undo all the processes in the digital domain, and that is how we have been demonstrating up to 1 terabits per second. But in all this digital signal processing, imagine this has to happen at high speed. It has to happen on an FPGA board or a ASIC in a real system, but it has to happen at really high speeds, at the baud rates which are at 25 gigabaud, which is happening at 40 picosecond time scale. You have to process this information really very fast. And what we found was that the most computationally expensive items here are this chromatic dispersion compensation and the nonlinearity compensation. This is the most computationally expensive repairing algorithm. And we started thinking, can we do something in the optical domain so that we can avoid applying digital signal processing for these two impairments. For the rest of the impairments, we can, might as well use, digital signal processing algorithm. That will reduce the computational complexity. And when you reduce the computational complexity, first of all, the latency improves, the power consumed improves, and so on. There's a lot of benefit there. So that's where the idea of optical processing comes in. Instead of doing digital processing, can I do optical processing? Can I take care of these impairments in the optical domain? And first, let's just, before we go on to doing that optical domain, you will understand it, how easy is it to do in optical domain if you just spare a moment to understand what the chromatic dispersion is doing to you. So let's say, for convenience, I've just shown you, on-off keyed signal in a standard single mode fiber. This representation shows you the constellation. If it is just on-off keying, it simply means that the pulse spreads. And so at this point where you were to take a decision, it was supposed to be 0, but because of this pulse spreading, you will read it as 1. So what you had sent as 11101, you would read as 111. This is the simple on-off keyed system. But what happens as a result of, in case of a QPSK constellation at the transmitter side, I mean, this is a simulated result. After 10 kilometers, because in an experiment, I cannot isolate only chromatic dispersion. The other impairments are also there, right? So I can only simulate to show you how the impact of chromatic dispersion is. You have a particular baud rate, 25 gigabaud. You have QPSK transmission. This is how the amplitude spreads. Amplitude spreads and also the phase spreads. And you see the amplitude completely spreads at the receiver after about 30 kilometers. Right? Sorry, this is about 100 kilometers. So after 100 kilometers, the pulse spread is about, if I were to look at the spread, it's about 680 picoseconds, which means that the information of this particular pulse is available at the 680th, or rather, if I divide it by the bit rate, and if the bit rate is like, let's say, it's 25 gigabaud, so 40 picoseconds, right? So you will get something like 680 divided by 40, so that will be about 17, which means the information that is available here spreads to the 17th neighboring pulse. So the 17th pulse after the first pulse is also seeing the information from this pulse, and that is not what you want to do. Was there a question? Okay. So This is the effect of chromatic dispersion. Now, how do I correct for it? I resort to my basic propagation model, which says that this is a part of the nonlinear Schrodinger equation. It's not nonlinear yet. It's still the linear chromatic dispersion effect. It's a second order differential equation that explains how the amplitude varies as a function of position. And you know that beta 2 represents the dispersion parameter, right? So chromatic dispersion parameter. And this is how it affects the pulse. So the transfer function corresponding to this is, how do I write the transfer function now? You just replace that del A by del T with j omega because you're doing a harmonic analysis. And then you will write the input output transfer function as e power minus j beta 2. Omega square came in because you have a del square by del T square and z. So this is what the transfer. So I'm going to look at it now as an input output and a transfer function. And the transfer function in the frequency domain is this. Once I have the transfer function, and if it is a linear system, how do I invert the transfer function? Whatever I get in my receiver, I just have to multiply with the inverse of the transfer function. So I should get back what I transmitted. So it's a simple enough equalizer we can think of. The equalizer is 1 over this transfer function. So instead of minus j, you have plus j. So all what you need to do to correct for chromatic dispersion is, mind you, you're doing it in frequency domain. So you find the FFT of the received signal, multiply it with this equalizer transformer function, convert it back to time domain, you get your original signal. So actually, correction of chromatic dispersion in the digital domain is very easy because we know the transfer function. What is the challenge? The challenge is that we have to do this FFT and IFFT operation. And this Fourier transform operation is probably the most expensive digital signal processing operation because it requires several multiplication and addition operations. So even though it is possible and people are doing this, as you go to higher data rates for longer distances, it is better to avoid this process. Now, why are we talking about nonlinear effects? You know, I can always avoid nonlinear effects by saying that now let me propagate it low power. Right? Low power, there's no nonlinear effect. I just pretend that there is no nonlinear effect. Everything is in the linear world and be happy with it. But suddenly, off the last few years, people suddenly started talking about nonlinear effects in fibers. I mean, in communication fibers, right? It was not a problem at all earlier. The reason is the following. So this plot shows the bit error rate, the number of errors that you count as a function of the transmitted bit, as a function of signal to noise ratio. This is one standard plot that you use to compare different transmission systems, right? And the acceptable bit error rate is marked here. It is about 10 power minus 3. Beyond that, there are these error correction codes which will take care of correcting for it. So this blue line corresponds to the bit error rate versus signal to noise ratio, which means that if I have a signal to noise ratio of 10, it means the bit error rate for a QPSK transmission system is fixed. Similarly, this is for a polarization multiplex QPSK. This is for 16 QAM. This is for polarization multiplex 16 QAM. What is 16 QAM? Instead of transmitting 4 constellations, you're transmitting actually 16 constellation points. 4 levels in amplitude, 4 levels in phase. So you get 16 combinations, 16 possible combinations. What you see here is very interesting. If you're going higher and higher in constellation, the green line is my reference line, which is my required bit rate. So to required bit error rate. So to maintain this bit error rate, it means that if I were to transmit 16 QAM, I need a signal to noise ratio of about 16. Whereas if I were to do QPSK, my signal to noise ratio requirement was very low. It's very intuitive to understand this because as you're transmitting more constellations, the constellations become more susceptible to noise. What is the x-axis? It is a signal to noise ratio. So decreasing signal to noise ratio means more noise. More noise is more uncertainty, right? So the uncertainty that is allowed in case of higher order constellation is actually low because you are packing the entire constellation with specific phase requirements, right? So to be able to do an error-free transmission, you need a larger signal-to-noise ratio. And how do you increase the signal-to-noise ratio? There's nothing you can do about the noise in the system. All what you can do to improve the signal-to-noise ratio is to increase the signal power. Now, the moment you have increased signal power, what happens? Your non-linearity kicks in. So, this is the standard nonlinear Schrodinger equation part, the nonlinear part of that equation, where the nonlinearity is quantified through gamma. Professor Tyagarajan's lecture would have given you this idea. So, gamma is related to the nonlinear parameter, the effective core area, and so on. And that's fixed for a standard single mode fiber. It simply means that the phase that is added, which is gamma mod A square, right? That is decided by the mod A square, which is decided by the intensity. So larger the power, you wanted to transmit higher order constellation, so you wanted to put in large power. The moment you put in large power, you start kicking in nonlinearity. So this is spectral efficiency versus signal to noise ratio. So this is again Shannon's limit coming back. Shannon's limit, as I said, predicts that the capacity of a channel, which is number of bits per hertz that you can transmit in a channel. This is from Shannon's theorem. But in a fiber, of course, Shannon did not do this for fiber. This was done later. But there's a nonlinear limit, because as you increase the signal to noise ratio, the power increases, and the power increases, this phase noise increases, and because the phase noise increases, the capacity starts dropping. So it's not just good enough to have a good signal to noise ratio. So you do have complex algorithms to compensate for nonlinear effects. So there are back propagation algorithms. Basically, you invert this equation. Just like how you inverted the dispersion equation, you can invert the nonlinearity equation and get back propagation, but then it's again a very complicated algorithm. People are talking about machine learning algorithms, people are talking about genetic algorithms, but all are complicated to implement in high-speed communication systems. That is why, let's get back to the question, can this be compensated optically? If there are any questions, I'm happy to take now, because we are almost at halfway in the talk. Okay, I can continue?
Yes.
Okay. So, as I've already told you, the motivation for optical signal processing, increase in data rates, faster processes, larger energy consumption. If you can make use of nonlinear effects and carry out some of these signal processing functionalities in the optical domain, that is an ideal solution for the commercial communication world. But then what should you take care of? This is again from Peter Windsor's Bell Labs report. It should, whatever optical signal processing scheme that you are suggesting for an optical communication system, it should not depend, it should be impervious to time domain, frequency domain, polarization domain, phase front domain. You should not come up with a solution that works only for certain polarization, or you should not come up with a solution that will work only for wavelength domain. It cannot work, only for specific wavelengths, right? So whatever solution you're suggesting should be impervious to all this. It should work for all different modulation formats. It should work for different granularities. You should be able to process the entire data. You should be process the group of bits. You should be able to process frames and so on. Right? This is the ideal optical signal processing requirement table. So some of these, I'll not get into the details of this. I've already given you an explanation for this. We have demonstrated some of this, but what we're going to talk about is dispersion and nonlinearity compensation. So we know that now the dispersion and the nonlinearity are acting together. So we're going to use the good old optical phase conjugator. Now, optical phase conjugator is nothing new. It's been there since 1970s, where people used optical phase conjugation to. You would have studied in Boyd's book or Agarwal's book that you can use optical phase conjugate mirrors to correct for aberrations when you're trying to transmit wavefronts over very long distances, especially you're trying to image the sky and things like that. You can use phase conjugate mirrors to so that it will be self-healing. We are just using that in an optical fiber system, right? So there's nothing dramatically new in the theory. You write down the nonlinear Schrodinger equation. It looks like this in the first length of fiber. You put in a phase conjugation stage. So from this, in the second length of fiber, it's a phase conjugate that is propagating, And because it is conjugate, you're basically conjugating the entire equation. So this becomes plus j and this becomes minus j. So the key here is whatever phase got distorted or turned here, you're turning it in the opposite direction in the second length of fiber, which means it's like a self-healing phenomena. Doesn't happen very naturally this way. You have to make sure that the beta 2 L1 of the first fiber and the beta 2 L1 of the second fiber, essentially the beta length product should be the same, and this condition also should get maintained, essentially meaning that you should have identical lengths of fiber with identical gammas and identical powers launched into the fiber. Then this idea will work. So there's how do you generate a phase conjugation? This is very trivial as far as physicists are concerned, nonlinear optics people are concerned. All what you need to do is allow four-way mixing to happen in a nonlinear medium. You send in a signal and a pump. You get a conjugate, which is at twice omega p minus omega s frequency. You get an idler, which is not of any use. You're interested here only in conjugate. So in one half of the fiber, you transmit signal. In the phase conjugation state, you generate this whole set. You filter out the conjugate and then transmit through the second length of fiber. You don't need to do any dispersion or nonlinearity compensation in the digital signal processing. This transmission itself will take care of or will self-heal the phase changes because of dispersion and nonlinearity. What is the challenge now? I mean, this is a very new thing. I mean, I am talking about physics of 1970s. What is the challenge here? The challenge here is how do you now do it in a very compact medium? You can't do free space. You can't do really high power. You can't use high power Q switch laser for this. It has to be energy efficient. The energy that I spent for this process must be smaller than the energy that I would have used to run the digital signal processing. It should be modulation format independent. It should be wideband. It should be having a noise retention properties. By doing this process, I should not degrade the quality of the signal at this point. So people have done this with highly nonlinear fiber. People have done with other nonlinear, periodically pooled lithium niobate, essentially by making use of second harmonic generation and so on. But we started looking at it in a different way. So these are some examples of earlier demonstrations of what people have done with this is DTU work on a silicon waveguide, very poor efficiency. Periodical pole lithium niobate is being used in Japan a lot. They have even modules for this, but again, the power levels required, optical power level required is about hundreds of milliwatt, which means the electrical power required to generate that hundreds of milliwatt is really high, and so on. Again, highly nonlinear fiber is also used in this work, but also requires very high power. It's either using Chi2 or Chi3 mechanism. What we have done over the last 10 years, all our optical signal processing, we know that it is not energy efficient in all these three mechanisms. So all our optical signal processing is done with nonlinear semiconductor optical amplifiers, which is just a laser where you strip out the mirrors. So that becomes an amplifier. So it's as readily available as laser. I mean, you have to, of course, do the processing correctly to remove the mirrors, but then that's a semiconductor optical amplifiers. The mechanism of nonlinearity here is slightly different. It is not a Chi2 or a Chi3 because it's a semiconductor medium. It's not a dielectric medium. So you can't talk about Chi2 and Chi3 in a semiconductor medium. There's carrier density population. I'll explain briefly what the mechanism is. And the most important thing is, it is highly flexible for photonic integrated circuits. You can grow this along with other photonic integrated circuit elements, maybe the modulators, maybe the receivers, and so on, so that you get a compact nonlinear medium. This is the structure of a semiconductor optical amplifier. So you have a P-type, N-type. This is like a laser forward biased PN junction. You have emission coming in from here. You send in a current. You create a population inversion, and so on. It has a broad band. It's no different from a laser, except that it doesn't have a cavity. This is what happens. It's an amplifier, and the reason why people do not use this as an optical amplifier is because of this nonlinear behavior here. Means that as you increase the signal power, input power into the amplifier, the gain of the amplifier saturates. Why does it saturate? Because it's very simple. You have only a certain number of carriers that are available. Once you have used up all the carriers, you're not going to get the same kind of gain. So that is simple gain saturation mechanism of a semiconductor optical amplifier. But then if you're operating at this point, the response of the semiconductor amplifier is nonlinear now, and it's this nonlinear response you're going to make use of to generate 4-loop signal. Okay. So what is the mechanism? So this is what you're doing. You send in a signal and a pump through the semiconductor optical amplifier. Now the carrier density in SOA, so you know it's a semiconductor medium, so there is this carrier in the conduction band. Now this carrier density will now respond. Carrier density cannot respond at the pump and the signal frequencies because you know pump and signal frequencies are in terahertz. So the oscillations of carrier density does not really happen in terahertz. It can but respond to the beat frequency, which is omega s minus omega p. So what happens is the carrier density is now undergoing, is experiencing omega p and omega s and a beat frequency which is delta omega, which means that the carrier density in time, there is a grating formed. The grating formed in time because this is a beat, optical beat. Now, the beauty is the carrier density is related to refractive index. So whenever you have carrier density varying as a function of time, it means that the refractive index also varies with time. So imagine that now this SOA is behaving like a medium, which is a time grating. Now, what's the consequence of time grating? So this is a representation of the time grating. The average refractive index plus a phase modulation, delta n modulation. So what's the consequence of delta n modulation? Whenever there is a change in refractive index, there is a change in phase, which means essentially this SOA is working like a phase modulator. Okay, and the phase modulator, the frequency of response of the phase modulator is simply decided by the frequency spacing between the pump and the signal. So what will be the response at the output? You will have, it's a phase modulator, so you will get some frequency and you have a difference frequency, and you get some frequency of omega p minus omega, you will get a difference frequency omega p s minus omega, and you will of course have additional components, but we are interested in the conjugate, which is 2 omega p minus omega s. Now turns out that this is bitrate and modulation format independent because it is the carrier that is generating this. So it doesn't matter what your modulation is, this beat is formed at this beat frequency, and hence the conjugate is independent of this modulation format and also the bit rate. Is it good enough? Do you get sufficiently large conjugate power? So what we have done is we generally did it in a CW condition. This is experimental results from now on. As you keep changing the detuning between the pump and the signal, you change this detuning between the pump and the signal. What you see in this red is the conjugate. In fact, it is a conjugate conversion efficiency, which means conjugate power divided by input signal power, right? So you see that as the beat frequency becomes closer to 0, which means as the signal gets closer to the pump, you will see that the system starts responding very well, and you have a large conversion efficiency. In fact, you are seeing a conversion efficiency of about 10 dB, which means you get 10 times more the conjugate power at the output than the power that you actually gave at the input, which is very good conversion efficiency. It's not possible in a passive medium like a highly nonlinear fiber, and you are getting a large conversion efficiency because this conjugate is also getting amplified in the system because it's an amplifier, right? That's why your output power of the conjugate is large. This is the signal gain. You see a large signal gain when the conjugate power is low, which means that the signal power is large when the conjugate power is low. And obviously, as the conjugate power starts going up, I mean, you have to respect energy conservation, so the signal power starts going down, right? But then you're not interested in the signal, you're interested in the conjugate. So you can fix your detuning, generate the conjugate, and then you can use the conjugate to propagate in the second length of fiber. What's the detuning? You can get, so there's a 0 dB reference line I have drawn where the conversion efficiency is 0, which means you get as power matters is what we have seen. So here the conjugate power is the same as the input signal power. So that's some kind of reference for us, and you can go up to a detuning of 75 gigahertz. Why is this detuning important? Because when you actually do it in a system, you have a modulation coming around it. So the modulation frequencies will appear around it. So I can't keep them very close because the modulation will start of course, there's no modulation in the pump, there's a modulation in the signal. So I need to take care that the detuning is greater than the largest baud rate with which I'm transmitting. This is with data. So I'll explain what this is to you. So this is for different power levels, right? So you see this dashed line. This dashed line is the input. So at different power levels, this is the spectrum. So this is the pump. This is the signal, right? And this is broad because now you have modulation. There is some QPSK modulation or something here. And this null corresponds to the location of the baud rate. And this bold line actually shows the output of the SOA. You see that the conjugate is coming up. So all what you need to do is to filter out this conjugate and propagate through the second length of fiber. So one more important thing we need to check is that while doing this process, the data quality, the bit error rate, the signal to noise ratio of the input, of the output should not be worse than the input. If it becomes worse, it means that the conjugator block has worsened my signal, and that's not acceptable in a communication system. Whatever you're inserting should be such that it does not degrade the performance, if not improve the performance. So the important metric before we start using it in a system is to verify what is the data quality at the output. So here is the input signal to noise ratio. This is the output signal to noise ratio. You will see that up to about 25 to 30 dB, they are all falling on the same straight line. And 10 dB to 25 dB is the signal to noise ratio. If you remember in this plot, in Shannon's theorem, we saw that 10 dB to about 25 dB. This is the range of signal to noise ratio that actually works in a communication system. So long as you have retention of OSNR in that range, we are absolutely fine. So that is what this plot shows. It degrades outside this simply because SOA is a non-parametric system. There is an amplified spontaneous emission. So when you go in with an excellent data quality, which is like 30 dB SNR, the SOA starts adding some noise, and that's why this performance is degraded for a conjugate. This is again bit error rate of back-to-back versus signal versus conjugate. There is some penalty in signal to noise penalty, which is almost, sorry, this arrow is misplaced, but then at the 10 power minus 4 BER, it is less than 1 dB. Considering the benefit that we are going to get with this, we are ready to live with this because we can always compensate for the signal to noise ratio penalty by increasing the power. Now, I can always increase the power and the SOA is going to take care of all the nonlinear effects. So this penalty is not a bottleneck for me. The next evaluation is it has to be wavelength independent. It has to work for all the C-band, right? It cannot work only for specific frequencies. So this is the performance evaluation across the C-band. You see the difference in the OSNR between the input and output that is almost constant at all these wavelengths measured across. And the penalty is also almost constant. This 1 dB penalty or 1.5 dB penalty, what we saw, that is almost constant. The largest is 1.5 dB, but here you have 1 dB. That's almost constant across the C-band. I will skip this polarization insensitive conjugate generation because we said that the way the polarization, way the system has to work, it has to work for both the polarizations also. So there's a little bit of theory here, but I'll skip this in the interest of time. All what we need to understand here is that to generate a polarization insensitive conjugation generation, you need two pumps, one which will take care of the X-polarized signal, another which will take care of Y-polarized signal. So first, instead of one pump, we will use two pumps, both in the bidirectional configuration. So you put two pumps in the orthogonal polarizations into the SOA and signal which is polarization multiplexed in the forward direction. That gives me the conjugate in both the polarizations. So this is a schematic of the experiment. It looks a bit scary, but it's actually not. So this is the coherent transmitter. You have, it goes through the port 1 of the semiconductor optical amplifier. This is the pump whose X pole and Y pole is split. The X pole goes from the port 1. The Y pole actually goes from port 2. And you generate the conjugate in port 2. That is what you are interrogating in the receiver. So turns out that There's no penalty between the X polarization and Y polarization. So this is black is X polarization, blue is Y polarization, and the conjugate actually falls on, I mean, there's no, we are able to extract both X and Y polarization without penalty. Now the real test is testing it in an optical link. In an actual link, does it work? This is all back-to-back condition, right? We have demonstrated that it is insensitive to polarization, it is insensitive wavelength, it is insensitive to modulation format. Now we need to see whether it will actually work in a link. So you generate 21 gigabaud QPSK and 16 QAM signals. Both these modulation formats we have tried. Transmit through one span. Do a conjugate generation in the middle with the SOA. So SOA is like a laser. You just send some current through it. That's good. You send pump through another laser. Then the power required is only 1 milliwatt. It doesn't require hundreds of milliwatt, unlike other nonlinear media. Then it passes through the second span. So this is the input, which is pump and the signal. After the SOU, you have pump, signal, and the conjugate. And you filter out the conjugate. This is the filtered conjugate. You throw away your pump and signal, transmit through the second half of the fiber, interrogate in the coherent receiver. This is what happens. You see the red lines are back-to-back case. That's a reference for us. And blue is a back-to-back conjugate, again, is a reference for us. This triangle is the results when you do not have OPC, which means you're doing digital signal processing for complicated inverse Fourier transform operation to recover the signal. And this OPC is 50 kilometer, OPC 50 kilometer, which means you transmit through 50 kilometer, then you do a phase conjugation, then you transmit through the next 50 kilometers, you have this. So you see the penalty is less than a dB. You see the scale is 10 to 12, the penalty is again less than 1 dB like what we have shown in CW. And as I said, this 1 dB penalty is not critical because we can always increase the signal power. So what happens when you increase the signal power? So this is where you increase the signal power. When you increase the signal power, the OSNR of the receiver already improves, right? So as you increase the signal power, you see the blue, the red is where you have without OPC, that you're trying to do dispersion compensation. The penalty shoots up beyond about 4 dB power. You see it increases very much. And this is the effect limit. I mean, you cannot recover the data beyond that. Whereas, and this is how the constellation looks like with this penalty. But in the presence of OPC, which is blue line, you see that you are getting much better performance for much larger pump powers, which means you are able to transmit much larger pump powers through the fiber the moment you had optical phase conjugation in between. Similarly, we did this performance evaluation for 16 QAM and similar results were observed. We did this not just for 16 QAM, we also did for this other modulation format, which is very popular, which is orthogonal frequency division multiplexing, coherent OFDM. In wireless, it is very popular. It is getting popular in optical communications also. So even for that format, the results are true. And of course, the data in different, across the C-band, the performance is the same. So the last but not the least is energy implication. All this process, how much energy did you use? So we did a stock checking of what is the energy actually consumed. The total energy comes out to be some number, 175, roughly around 175 watts. But if you just say that 175 watts, oh my God, that's a lot of power. But what matters here is if you're trying to do it for on-off keying, it is not energy efficient. But if you increase the data rate, what matters is energy per, it's not the power that matters, it is the energy that you spend per bit to process the data. So the energy per bit is what matters. So as you increase the baud rate, we have proved that the whole system is impervious to data rates, which means that as the data rate goes high, you know that the power remains the constant, the data rate goes high, so the energy actually starts falling per bit. The energy per bit starts falling. So the energy required for, in case of digital signal processing, the energy required for optical to electrical conversion will actually increase with baud rate, whereas here it actually decreases with baud rate. So these are going to be excellent solutions when we are working at, today the state of the art is 56 gigabaud. Very soon, in next 2 to 3 years, we're going to see 96 gigabaud systems. And for 96 gigabaud and beyond systems, the optical processing is going to be much more energy efficient than doing all this in PSP. So to conclude, we discussed some challenges and some solutions with optical signal processing. And we found that the noise-free, compact, modulation format dependent, polarization independent, modulation format independent, polarization independent, wavelength insensitive operation is possible with SOA. And we discussed phase conjugation and this its application with SOAs. I'm not discussing other SOA-based optical processing, but in the past we have published clock recovery with SOA, wavelength conversion with SOA, polarization multiplex wavelength conversion with SOA. The recent work is here, what is currently ongoing. Can we do a phase-sensitive amplification? Can we have an amplifier which does not distort the phase? Can we do phase quantization with SOA? So these are some of the recent work, and we'll be happy to discuss it at another opportunity. I cannot close this talk without acknowledging several factors that has contributed to this expensive experimental setup. We are probably the first institution, educational institution in the country to have this high-speed optical transmission test bed. So you're welcome to visit, and we are welcome to use this facility if you have sound research idea. This was funded primarily by the Office of Principal Scientific Advisor to the Government of India. The current project on space division multiplexing is funded by MIT. And of course, there are different fundings coming from SERB, DRDO, and our own institute. These were the people who were students who worked in the area of optical signal processing. So Arvind finished his PhD doing wavelength conversion, Manas did clock recovery. Today's work is primarily Anisha's work on phase conjugation and Lakshminarayan's work. Smaranika is working on space division multiplexing and nonlinearities in space division multiplexing. These are the two new students who are going to follow. All these people are going to graduate in a month or two. We're all waiting for the pandemic to get over, and these students will actually follow up this work. Again, I should thank all the collaborators where we had discussed at different stages through different projects, and thank you very much. This is what you would